Hello and welcome to this talk about SociTrack, a platform for autonomous social interaction tracking via wireless distance measurements. I would like to start off by talking about the elephant in the room, COVID-19. It has forced this conference to be virtual and severely affected our lives in countless other ways in the last few months. One measure to contain the virus, which governments and agencies around the globe have been enforcing, is social distancing, the simple act of not closely interacting with others and remaining apart. While this logic has been accepted in most countries, the specifics vary. From a suggested minimal distance of 1 to 1.5 to 2 or even more meters, health agencies have proclaimed different suggestions on how people should behave. One of the primary reasons for this discrepancy is the severe lack of scientific studies on the subject. Without a detailed knowledge of how close together over which period of time people must interact for the virus to spread with a high probability, policymaking must rely on educated guesses. We believe that enabling long-term experiments on people's interaction in their daily life could provide the necessary facts for a more rigorous, scientific approach to these health questions. But the demand for human interaction tracking is much broader than medical investigations. Among others, childhood development specialists are seeking a better understanding of the impact of physical proximity between caretakers and infants. They are interested in measuring and analyzing data on topics such as the frequency of interactions, the intimacy of pairs of people, and the dynamics of who initiates interactions. Similarly, researchers studying workspace dynamics investigate methods to improve our everyday interactions in the office. Among others, they seek data on the length and frequency of conversations, the extent of team working and how it differs between groups, and whether everyone is treated similarly. Using sensors to analyze our bodies as we get older is getting increasingly common. Through automated systems that track the interaction of elderly people, we can verify that they keep themselves in physical and mental shape through regular exercise and social calls. A detailed understanding of these behaviors might even help in detecting changes in these patterns, which can be a precursor for Alzheimer's. When we talk about suitable systems for interaction tracking, we are primarily interested in two features. The available measurement accuracy of spatial distances is a key metric for proximal interactions. While many systems provide room-level proximity, that is, whether we are in the vicinity of someone else, many of the aforementioned application scenarios require a much finer-grained resolution in the order of decimeters. For example, in the caretaker-infant scenario, it is essential to gather whether they are within touching distance of each other. On the other hand, the flexibility to move around and still maintain data collection is challenging. Most systems can only operate in single-instrumented rooms where infrastructure has been deployed. However, this is clearly not sufficient if we seek to investigate how people behave throughout their everyday lives, wherever they might be. Bluetooth Low Energy, abbreviated BLE, is a ubiquitous technology which is supported in literally billions of systems and often permits users to track each other through their mobile devices. Unfortunately, its accuracy is lacking as it relies on the received signal strength and therefore can only provide coarse granularity. Ultra-wideband radios, abbreviated UWB, on the other hand, use the travel time of packets to determine the distance utilizing the speed of light. This drastically improves measurement accuracy at a trade-off with high energy costs. Countless other infrastructure-based solutions find ways to achieve a good balance between these two extremes by pushing most of the complexity to fixed installation. This causes blind spots in environments which cannot be covered and is therefore infeasible for large-scale studies. Instead of focusing on a single technology, we have been wondering whether a combination of techniques could enable us to obtain a solution that is both highly accurate without restricting mobility in any way. This presents us with four major challenges that a general-purpose interaction tracking system must address to support a wide variety of applications and use cases. We must first find a technique that allows us to acquire decimeter-accurate distance estimates at up to multiple hertz to enable detailed studies of interactions. Secondly, our solution must not rely on any external infrastructure and must remain autonomous to enable in situ experiments. Thirdly, due to the frequent changes in positions of devices, they must constantly monitor their environment and quickly detect and join networks to capture the natural clustering of people on the study. Lastly, our solution cannot use techniques that rely on line of sight, as devices should be worn below clothing and should not fail due to obstacles. So let's start with measurement fidelity. As previously mentioned, UWB uses the time of flight to estimate the distance between devices. While there are also other upcoming techniques which attempt to achieve the same, UWB is uniquely suited for this purpose through its distinct wide bandwidth. With at least 500 MHz per channel, UWB sends extremely narrow symbols. This is highly beneficial to avoid the adverse effects of multipath reflections from walls, which overlap for traditional radio symbols and therefore allow us to precisely recover the time of arrival for UWB. However, out-of-the-box UWB does not solve the problem. The issue is that while the measurements are very precise, they can be systematically off. So-called small-scale fading effects can cause destructive interference for a single frequency band at a specific location. Similarly, antenna nulls can impede the transmission and reception quality. This causes UWB to produce highly precise measurements for a single channel, that is, a given frequency and antenna position, that do not correctly represent the distance between devices. This is seen in the plot, where the correct distance would be 3 meters, but the estimate is off by more than 1. But this also holds if we vary frequencies and antenna positions. As we can see, all measurements for a single channel are tightly grouped but do not correctly represent the ground truth of 3 meters. Diversity ranging leverages multiple antennas as well as multiple frequency bands to avoid these issues. Previous work has been proposing 3 antennas and 3 frequency bands for a total of 27 different channel estimates. These are then combined by taking the 30th percentile to produce a single estimate that is both precise and accurate. The second challenge is enabling infrastructure-free deployment. To achieve this, we must reduce the high energy costs of UWB as much as possible. Due to the many samples that diversity ranging requires, the number of packets that must be sent is high. However, there is room for improvement in current state-of-the-art protocols. Due to the ping-pong of packets that is required for time-of-flight ranging, protocols use unicast messages between devices, where each device receives a response from n others, resulting in O of n squared message complexity. Secondly, responses in previous protocols were simply transmitted by sending after a random backoff. This results in an inefficient use of the channel and causes collisions and retransmissions. Lastly, because responses are not scheduled, everyone who hears the message always responds. This results in measuring each distance in the network twice. To avoid these inefficiencies, we strictly schedule all nodes and exclusively use broadcast messages. This allows us to reduce the message complexity from quadratic in the number of nodes to linear. Furthermore, nodes have a guaranteed slot where they can send. This knowledge enables other nodes to avoid listening for long periods of time while waiting for packets. As we now know when each node responds, a device must not listen for all responses, but can directly go to sleep after it has done its job, thereby eliminating redundancy. These improvements result in UWB ranging, which is more energy efficient, scalable, and reliable. Still, while the energy costs of the ranging protocol have been reduced, UWB remains poorly suited for constantly searching for new neighbors, which is a necessity to reliably detect the arrival of new people in the vicinity. Its receive power draw is higher than any other radio technology that is suitable for sensor networks, and the ranging on the same frequency band would constantly interfere with network discovery packets. In addition to this, infrastructure-free solutions would not have the ability to send data back while experiments are still running, as UWB cannot connect to other existing devices. Therefore, we choose to add a second radio which uses Bluetooth Low Energy. With its significantly lower energy consumption that is designed for periodic transmissions and receptions, it is perfectly suited for discovery. The use of an independent radio also allows us to separate the ranging and discovery aspects in hardware, resulting in a simpler and more robust system. With BLE, we have the benefit of connections to many commercial devices, such as smartphones and laptops, which can then forward our data in real time. This dual radio architecture enables infrastructure-free deployments through an efficient discovery mechanism, and in addition permits us to opportunistically use external devices for remote access. To support high mobility, nodes must be able to quickly create or join networks. To do so, they periodically advertise both their own ID as well as the network they belong to. If two devices which do not belong to a network yet discover each other, they form a new one. In case one of them already belongs to a cluster, the new node will directly join. A more complex situation occurs when two clusters encounter each other. In such a case, the one with the higher network ID will prevail, and newly joined nodes will start spreading knowledge about the cluster. As clusters grow in size, not all nodes can directly communicate anymore, but are still part of the same network. Traditional multi-hop solutions require routing which must continuously adjust and stabilize in the presence of mobile nodes, thereby causing disruptions. Protocols that avoid networks by only communicating with their neighbors cannot coordinate and hence again inefficiently use the channel, which limits the samples per second we can get while nodes are on the move. Lastly, as most network protocols use static contention slots, a sudden appearance of many join requests, such as when clusters merge, causes long delays. Luckily, the concept of synchronous transmissions, where messages are concurrently flooded through a network, permits us to use a communication primitive that is topology agnostic and highly reliable. It further synchronizes the nodes and allows us to use an efficient TDMA scheme. By adding the ability to dynamically adjust the number of contention slots depending on the number of join requests, we can create a protocol that supports high node mobility and is still scalable. For social experiments, it is essential that the subjects under investigation are not constantly aware of the fact that they are being observed, as this often leads to an artificial change in behavior. Therefore, it must be possible that people wear the sensors how they feel most comfortable with, which is oftentimes below clothing or obstructed by arms and backs. This has a negative impact on any sensor technology that relies on signal strength or direct line of sight. For the same reason, experimenters should try to not interact with subjects, which makes it hard for them to verify and monitor a running deployment and limits the possibilities to automatically collect data. These problems can again be solved through our dual radio architecture. Using radio frequency time-of-flight ranging, we can maintain stable measurements despite obstructions and varying environments. PLE allows us to connect to devices in real time for debugging and enables smartphones to serve as relays to collect the data while a long-term experiment is still ongoing. With this, SociTrack reduces demands on the subjects in how they use the tool and reduces the burden on experimenters by supporting autonomous deployments. After having demonstrated the rationale behind our dual radio architecture, we now show the task separation in action. Through periodic beacons, two nodes discover each other and start a network. To join, one node listens to the network schedule and then sends a join request. Thereafter, the nodes are ready to start ranging. In the next round, they first send their respective initial requests over multiple channels to achieve diversity. They then respond with broadcast messages and compute the time it took the packets to travel the distance between them. Notice that the BLE advertisement continues in parallel and permits the direct offload of data to external devices. To summarize, BLE ensures that nodes are aware of each other and are part of the same network. It further assists with interacting with other devices. UWB focuses on the ranging and schedules slots in a multi-hop network to efficiently measure distances between all nodes. So let us put the system to the test. We have been actively using SociTrack in the field in a collaboration with researchers which study caretaker-infant interactions. In this video, the infant is wearing the device in a specialized vest on his chest. The father in the corner has the device stored in his pants pocket. What we observe is the so-called strange situation procedure. The graph at the bottom displays the caretaker-infant distance and shows how the infant retreats to his caretaker when he feels insecure. The interactions between all three individuals are relevant here. We see that after the infant is being comforted by his father, he accepts the stranger and continues exploring as seen by the large distance to the father. However, when the stranger tries to initiate an interaction and join the play, the infant once again retreats to the father, visible by the second dip in the distance between them. SociTrack enables us to collect such measurements over a long period of time directly in many households, without researchers having to set up and maintain infrastructure. Next, now that we have addressed the 4 challenges in the system design, we verify that we successfully resolve them in practice. We find that diversity ranging is key to obtain reliable results. The different combinations of channels display tightly grouped results, which are oftentimes consistently biased to a specific environment. Notice that these devices have been calibrated before, but due to the highly local effects of small-scale fading and antenna orientation, it is impossible to find an optimal channel that fits all environments. However, by aggregating over all of them, we find that we can significantly boost accuracy and precision. This graph displays the raw ranges of all channels over a distance of 3 meters as a solid line. We see that measurement errors are well below 1 meter with an accuracy of half a meter in 90% of the cases, but a long tail of measurements that are significantly off. The dotted line shows our results if we aggregate over the channels. As you can see, this allows us to reduce the 95th percentile error by almost 80% and achieve a median error below 5 centimeters. We have also verified this finding over multiple distances. In each of them, we observed that the aggregated results significantly reduce the error and provide measurements that are both precise and accurate. With this fidelity, we can match the results of infrastructure-based UWB systems such as SnapLock without sacrificing mobility. With a sample every 60 milliseconds, the ranging system furthermore allows us to easily track moving individuals, making SociTrack well suited for applications that seek both spatial and temporal resolution. The aspect that truly makes SociTrack unique is its independence of any infrastructure. To demonstrate that this enables us to cover all aspects of living, we instrument 5 people in our lab for an entire day. The graph displays the distances to a group of 4 nodes from the view of a 5th one. Spikes indicate that the distance to that node has changed significantly, such as when these people interacted with each other or left the shared space. Using our global timestamps, we map the measurements to known events and contextualize the data. We also see that while 3 of us go out for dinner to a restaurant in the evening, SociTrack seamlessly continues data collection without us having to adjust anything. To demonstrate the effectiveness of our dual radio architecture, we recreate a scenario where 2 clusters of nodes meet. In the first run, we disable the discovery feature, whereas in the second run, we use BLE advertisements to detect and merge the clusters. As you can see, the UWB ranging starts to interfere as soon as the clusters approach each other. This graph shows the distance between the 2 individuals of each cluster. Starting at 15 seconds into the experiment, cluster B experiences heavy interference and does not collect any more measurements. Similarly, once the 2 clusters stand close together for a meeting, also cluster A observes measurements that are significantly off due to the wrong reception of packets. Only after both clusters separate again, measurements can continue. When we enable discovery, we do not observe these problems. The 2 clusters approach and merge long before the clusters are in close vicinity, and clearly show all the interactions. After cluster B depart, the network again splits into 2 clusters and ranging continues. SociTrack can also allow us to automatically detect and analyze interactions, rendering manual actions by scientists obsolete. In this experiment, we instrument 4 individuals and observe them over a period of 10 hours. We find 81 interactions between the different pairs. The 2 bars in the plot display the data in both directions. Their consistency suggests that the results are robust. Notice that thanks to the fine-grained results, we can adjust our definition of what we consider an interaction in post-processing, something that is impossible with the binary proximity data of most systems. The highlighted interactions in the middle show individual 1 in a collaboration with 2 other individuals. From manual logs, which we can map to the data, we know that these pairs have been sitting, explaining the clearly closer interactions over a longer period of time. Lastly, let us consider the different application requirements and how SociTrack can adjust. To target a wide range of applications, our protocol is parameterized and an associated energy model allows for deployment time decisions of system performance. For example, despite a high sampling rate every 2 seconds, we can support large groups for multiple days of continuous ranging, as shown in the graph on the left. This is relevant for all interactions in locations such as the office or schools. On the other hand, if long-term operation is key, we can reduce the sampling rate and achieve almost 2 weeks of operation as seen in the middle graph. If nodes separate in between and stop ranging, our efficient discovery permits devices to work even longer. Finally, we can also trade off our high accuracy and gain additional days of operation if this should be desired. We consider SociTrack research-enabling research. We hope that a method of providing infrastructure-free, high-fidelity interaction tracking for mobile individuals facilitates others not just to ask more elaborate questions, but that our dual radio architecture opens up new possibilities altogether. This work has been done in a collaboration of researchers at ETH Zurich, UC Berkeley, and UC San Diego. You can find all our hardware and software publicly available on GitHub. If you're interested in using SociTrack for your research, please contact us. Thank you.